So what we've talked about so far are three different systems. We have talked about the phosphagen system, metabolic systems, by the way. We've talked about the phosphagen system. We've talked about fast or anaerobic glycolysis, and we've talked about slow or aerobic glycolysis. The differences that we've discussed mostly revolves around the rate at which they can resynthesize ATP, right? The phosphagen system can resynthesize ATP the fastest. Anaerobic or fast glycolysis can resynthesize ATP at the second fastest rate, and aerobic or slow glycolysis can resynthesize ATP at the slowest rate compared to these two systems. And let's say this right off the bat. I know we've already said it, but I think it's important to reiterate. Yes, aerobic or slow glycolysis can produce the most amount of ATP per glucose molecule, 32 approximately, but that says nothing about the rate over time that the system can resynthesize ATP. So one can imagine that depending upon the ATP demand of a cell, that's what's going to dictate which one of these systems the cell kind of utilizes the most, which system dominates. And the objective of this lecture here is to actually talk about different circumstances, all of the circumstances that we've actually already talked about already inside of a muscle cell, but now more so focus on what actually causes the cell to transition between these systems. And by that I really mean what causes one of these systems to dominate over another, because in reality all these systems are used simultaneously, but in different circumstances one of these systems will certainly dominate compared to another system. And that's the objective here, is to, I think we know in what circumstances what system would probably dominate depending upon the ATP demand, but to discuss what's actually going on in the cell to cause one of these systems to dominate. Let's go back to what we were talking about in the last lecture, which was like a jog or fast walking pace. Okay, so you go from a seated position to, let's say, a slow jog. All right. The muscle fiber's ATP demand is clearly going to rise compared to what it was, right? You're going to get a big rise in the ATP demand of the muscle fiber. And it's logical. It's not going to be what it was compared to a sprint, but it's going to rise. It's going to be higher transiently than the supply. So the demand of ATP will be higher than the supply. What's going to accumulate? ADP, inorganic phosphate, hydrogen ions, so forth and so on. Those metabolites, those products of ATP hydrolysis will begin to accumulate a little bit. Okay, what else is going to happen? Epinephrine is going to rise in your bloodstream. Calcium is going to rise inside of the muscle fiber, all the things that we've talked about. So epinephrine rises in the blood, calcium rises in the fiber, ADP rises in the fiber. Now what does that mean? Inside of the muscle fiber, without getting back into all of the explanations for this, epinephrine and calcium is going to cause glycogen to start to be broken back down into glucose, 6-phosphate. ADP is going to start allosterically activating many different enzymes. It's going to allosterically activate creatine kinase, which is the enzyme of the phosphagen system. That's going to be involved a little bit here, although it's certainly not going to be the dominant system in this circumstance. We'll explain why. It's going to allosterically activate phosphofructokinase, and it's going to allosterically activate enzymes of both the Krebs cycle and the electron transport chain. The point I'm trying to make here is when ADP accumulates, it's going to get all of these systems going that we've actually discussed. Not so much, we're not going to ultimately run here anaerobic or fast glycolysis for reasons you're about to see, but what is it doing? It's getting the phosphagen system going to some degree. It's certainly getting glycolysis going by activating phosphofructokinase. It's getting the Krebs cycle pumped up, all right? It's getting the electron transport chain going. Right? So immediately you should see here, all of these systems work together. It's not that these systems are mutually exclusive of each other. They're all going to get started once the ATP demand rises inside of a muscle fiber. What we really need to focus on, though, is glycolysis and figuring out in this circumstance, is it going to be fast glycolysis or is it going to be aerobic glycolysis? Let's say that better. Is it going to be faster anaerobic glycolysis or is it going to be slow or aerobic glycolysis? And I think you know the answer. It's going to be predominantly aerobic or slow glycolysis that gets used. But we need to figure out why. Like, why in this circumstance, where the ATP demand inside of the muscle fiber is kind of moderate. Again, this isn't a sprint. This is like just a kind of a slow jog. Why inside of the muscle fiber, when the ATP demand is elevated but moderate, does the glycolysis that's run end up being like an aerobic or slow glycolysis and not an anaerobic or fast glycolysis? That's the best I can do with the amount of time I have in this class in terms of trying to explain the difference between these two to you. So here's glycolysis. You've seen it a million times. What do we know right now? Glycogen is being broken back down into glucose 6-phosphate thanks to epi and calcium. Phosphofructokinase is being allosterically activated by ADP. So glycolysis is running inside of the muscle fiber, and it's producing pyruvate, it's producing NADH, and it's producing ATP. You know where the ATP is being consumed. It's being consumed by the muscle fiber. But what's going to happen to NADH and pyruvate? I've already told you in the previous lecture what happens to it, right? In this circumstance, it gets shuttled into the mitochondria to be broken down with oxygen. But we really want to understand why. Why is pyruvate and NADH going into the mitochondria and not becoming lactate and NAD again? What about this circumstance is causing pyruvate and NADH to go into the mitochondria? The first thing that you have to know in order to make sense of why pyruvate and NADH enter into the mitochondria under this moderate ATP demand circumstance is where they're going. That's the first thing that you have to understand. Where is the NADH going? It's going to the electron transport chain. What's going to happen to the pyruvate? It's going to be turned into acetyl-CoA, and NADH is going to be made, which is going to go to the electron transport chain. Where is the acetyl-CoA going to go? It's going to go around the Krebs cycle, and a whole bunch more NADH and FADH are going to be made, which are also going to go to the electron transport chain. So the NADH that's coming in is going to the electron transport chain. And basically everything that we're about to make from pyruvate is going to the electron transport chain. That's the first part of this that you have to understand if you want to understand why, in this circumstance, pyruvate and NADH come into the mitochondria. You have to understand that everything that's about to be made from them, and by them I really just mean pyruvate because you know exactly where NADH is going, but everything that's about to be made from pyruvate, it's all going to the electron transport chain. And so is NADH, and that comes in. And what's going to happen to it there? We don't need to go back through the electron transport chain for you to know exactly what NADH and FADH are going to do for the electron transport chain. They're going to power the electron transport chain, right? And they're going to power the electron transport chain so that ATP can be made through oxidative phosphorylation. That's what all of the pyruvate and NADH that's coming in is for the purpose of. Like, that's its purpose, right? The NADH is to power the electron transport chain, and most everything that we're about to make from pyruvate is also to power the electron transport chain, to make ATP through oxidative phosphorylation. All right, now here's the big part. What is going to allow for the electron transport chain to keep operating? Or let's say it this way, what's going to determine the rate at which the electron transport chain can operate? Yeah, allosteric activation of some enzymes, but the big one is oxygen, right? Oxygen is the final electron acceptor of the electron transport chain. The electron transport chain is only going to run as fast as there is oxygen available to it. And this should make sense, I hope, from the previous lectures, right? If electrons aren't being taken away from the fourth complex, then the electrons will accumulate in the chain, and the chain will get backed up and it'll slow down. So this chain, and thus by that I mean the electron transport chain and oxidative phosphorylation as a whole, is only going to operate as quickly as there is oxygen coming to it. You need lots of oxygen constantly coming to the electron transport chain to take electrons away from the fourth complex. Right? These electrons constantly need to be extracted from the fourth complex so that the electrons from NADH and FADH can keep moving through the chain. Oxygen dictates the rate of the electron transport chain. It's really that simple. People really struggle with this concept. And I mean, I struggled with it too at one point in time. So whenever I get to this point, I feel like I need to try and explain it in different ways, or so that people can really think about it and hopefully make sense of it. But it's somewhat difficult to do because this is highly conceptual and a highly visual process. You have to imagine that there's lots of NADH and FADH coming to, in the case of FADH, being created by the electron transport chain. Okay? So there's lots of electrons being brought to the electron transport chain through NADH and FADH. Okay? And these electrons are being shuttled throughout the chain. And the speed at which they can be shuttled throughout the chain is all going to be dictated by the speed at which electrons are removed from the fourth complex. So you constantly need sufficient oxygen coming to the fourth complex and removing those electrons from the fourth complex to allow for the electrons to continually move through the chain. And the speed at which those electrons can move through the chain is, of course, going to ultimately determine the gradient, the hydrogen ion gradient, and thus how much ATP is made through oxidative phosphorylation. So now you might ask, well, what are you getting at? And we have to think about the cardiovascular system for a moment. We're not by any means we're not by any means to the point of discussing the cardiovascular system in this moment, in this course, but you can still, I hope, think about this. Because you don't really need to know anything about the cardiovascular system for this, what I'm about to say, to make sense. What also happens when you begin to exercise to the cardiovascular system? Everybody knows this, I hope. Your heart rate increases, right? And the force of contraction actually increases too. The point is, when you begin to exercise, your heart rate increases. That means more blood is being pumped around your body. Why do you think more blood is being pumped around your body? To deliver more oxygen to your muscle fibers. That is, I mean, there are other things that are being delivered to the muscle fibers too. But for the sake of this discussion, when you exercise, what do? You breathe more to bring more oxygen into your bloodstream. We'll talk about the whole respiratory system in this course too. But you breathe more to bring more oxygen from the atmosphere into your blood. And your heart rate increases when you exercise to pump more blood and thus oxygen around your body to your muscle fibers. Now, why would you want to be pumping more blood and thus oxygen around your body during exercise to get to your muscle fibers? Well, if you understand the electron transport chain, it should make perfect sense. What is the electron transport chain receiving more of during this bout of exercise while you're jogging, right? Glycolysis is running faster, right? Because the ATP demand rose and that caused glycolysis to run faster. So glycolysis is producing more NADH. That's coming to the electron transport chain. Also, since glycolysis is running faster, more pyruvate is being made. That's entering into the mitochondria. And the pyruvate is being turned into acetyl-CoA, which is creating NADH, which is also coming to the electron transport chain. The acetyl-CoA is going around the Krebs cycle, and that's also making a whole bunch more NADH, which is also coming to the electron transport chain. The point I'm trying to make is, when you begin to exercise, there's a lot more NADH coming to the electron transport chain than there was before. Why? Because the rate of glycolysis has increased. If the rate of glycolysis increases and the rate of the Krebs cycle increases, you're going to produce a whole lot more NADH. Remember how I just showed you at the beginning of the lecture, ADP will kind of allosterically activate some enzymes of the Krebs cycle. So the Krebs cycle will pick up its rate as well. The point is, if glycolysis increases its rate, if the Krebs cycle increases its rate, the cell is going to be producing a lot more NADH than it was before you started that exercise, right? Because this is all because the ATP demand has risen inside of the muscle fiber. There's a whole bunch more NADH going to the electron transport chain. Now the question becomes, how are we going to ensure that all the electrons from all this NADH actually gets through the electron transport chain? We need more oxygen within the muscle fiber and thus within the mitochondria so that more electrons can be extracted from complex 4. That's what we need. That is why you deliver more oxygen to your muscle fibers during exercise. It's so that more oxygen can go into the muscle fiber, into the mitochondria of the muscle fiber, and begin extracting electrons from complex 4 at a faster rate. If you can extract more electrons from complex 4, right, at a faster rate, that's going to enable and ensure that all these extra electrons can actually move through the chain, right? Because there's a whole bunch more NADH and FADH within the chain during exercise for the reasons that we just discussed. There's a whole bunch more NADH and FADH than normal. That means there's a whole bunch of extra electrons trying to move through the chain. And to ensure that those electrons can all move through the chain at a sufficient rate, we need extra oxygen coming into the muscle fiber and into the mitochondria to remove extra electrons from the 4th complex. That was an accident there. And ultimately, what's the point of all of this? If you can move more electrons through the electron transport chain than normal, which is what's going to start happening when we're exercising, what are you going to create more of, or more over time of? You're going to create more of a gradient within the intramembrane space of hydrogen ions, and thus that's going to allow more ATP to be made through oxidative phosphorylation. And that's going to ensure that the ATP demand of the muscle fiber is met. When we exercise, and this, again, you relate this to exercise, but you can relate it to anything. Again, continuously, I always try to make sure that I'm not just emphasizing exercise. When the ATP demand really of any cell increases, what is it first going to do? It's going to try to increase its ATP supply through oxidative phosphorylation. That is step number 1 that the cell will do. Because you can make more ATP through oxidative phosphorylation than normal, right, than at resting levels. And the way that you do that is by bringing more NADH and FADH to the electron transport chain. You're providing more substrate to the electron transport chain so the electron transport chain can run faster and produce more ATP through oxidative phosphorylation. So let's say that the ATP demand rose inside of the muscle fiber to something, I'm just making up numbers, but 300 ATP per second. It's going to be in the millions, but 300 ATP per second. Okay? What the electron transport chain needs to do is ramp up so that 300 ATP per second can be made from the electron transport chain. And perhaps at rest, it's only 150 ATP per second being made, which meets the demand at that time. But then the ATP demand within the muscle fiber rises during this exercise that we're talking about. And we need to get the electron transport chain running at a faster rate so that the electron transport chain can produce more ATP via oxidative phosphorylation to meet that demand of ATP. It's really that simple. And the biggest thing that's going to ensure that this is possible is oxygen. Everybody always believed that this is the big limiting factor is to the electron transport chain, is oxygen. You need enough oxygen coming to the electron transport chain to remove these electrons to ensure that the electron transport chain can run faster and actually make enough ATP through oxidative phosphorylation to meet the demand of ATP. And what I can tell you is that during like a light jog, the demand of ATP within your muscle fibers can very easily be met through oxidative phosphorylation. What I'm saying is plenty of oxygen can come into your muscle fibers to allow for the electron transport chain to run fast enough to make enough ATP through oxidative phosphorylation to meet the ATP demand. If you think about what happens to your heart rate during like a light jog, right? It goes up, but it doesn't go up dramatically. Your resting heart rate might be 70 beats per minute, and during a light jog, really depends, of course, on the person, but it might go up to 110, 120 maybe, which is nowhere near your maximum heart rate. I mean, you're pumping more blood and oxygen around your body, but not that much more, because in reality, you don't need that much more oxygen to go into the muscle fibers to allow for the electron transport chain to run at a faster rate so that it will produce enough ATP to meet the demand. It's pretty easy to accomplish. The electron transport chain and oxidative phosphorylation would by no means be maxed out in this circumstance. And this brings us back to glycolysis. As long as the electron transport chain can keep running fast enough to consume all of the NADH and FADH that's being created, meaning enough oxygen is coming to the electron transport chain to allow it to run fast enough, then the pyruvate and the NADH that's being made by glycolysis is going to keep entering into the mitochondria because that's where it wants to go, right? As long as the NADH that's being created by glycolysis can enter into the mitochondria and be consumed by the electron transport chain, that's where it's going to keep going. And as long as the NADH that's going to be created from pyruvate through breaking it down into acetyl-CoA and running acetyl-CoA through the Krebs cycle, as long as that NADH that's going to be created from pyruvate can enter into the electron transport chain, then it's going to keep doing that. Okay? So what is going to cause then this anaerobic or fast glycolysis to set in? In a more advanced course, we would do this in many more steps than I'm about to do it. I just want to show you in the simplest way possible how and why this transition might happen. Okay, so imagine that you go from jogging to then trying to basically do something, not a sprint, but you start to run quite fast on the treadmill. For a healthy person, maybe that's like 10 miles an hour. Right? That's it. For most people, besides elite runners, 10 miles an hour is a pretty unsustainable rate on a treadmill. Okay, so you pick up the rate significantly, and what's going to happen is inside of the muscle fiber, what's going to rise? The ATP demand. Clearly, right? Because you've gone from a jog where the ATP demand was moderate to now asking the muscle fibers to contract much more frequently and much more forcefully than they were. So what's going to rise inside of the muscle fiber? The ATP demand, of course, is going to rise. If you go from a jog to something that is in between a sprint and a jog, like a fast, I don't know what to call this, running a lot faster. Let's not call this a jog anymore, it's a run, and a fast one at that. Some people might argue that a jog and a run are the same thing, so we're just going to say, at minimum, you pick up the pace significantly, and the ATP demand rises inside of the muscle fiber. Now what's happened? The ATP demand is now higher than the supply. Okay. You were meeting the demand of ATP during the jog through oxidative phosphorylation, but now you've picked up the pace significantly and the ATP demand is rising significantly again above supply. So what's going to accumulate? ADP. What's that going to do? It's going to allosterically activate phosphofructokinase. Additionally, if you increase the intensity of exercise, what's going to rise in the bloodstream? Epinephrine to an even greater degree. Epinephrine in your blood is proportional to the intensity of exercise. Second of all, what's going to rise inside of the muscle fiber? calcium. So what's the muscle fiber going to begin to do? Due to more epinephrine in the blood and calcium in the muscle fiber, it's going to break more glycogen down into glucose 6-phosphate. Due to the accumulation of ADP, it's going to start running glycolysis at a faster rate. All in all, as the intensity of exercise rises and the ATP demand within the muscle fiber rises, it's going to start consuming way more glucose through glycolysis. The rate of glycolysis is going to increase substantially, and you're going to produce more pyruvate, and you're going to produce more NADH. Now, naturally, this pyruvate and this NADH would like to go into the mitochondria, but I'm going to explain in this circumstance why that might not happen. So you have to think about where, as I've said, this NADH and pyruvate wants to go. Right? You're running glycolysis at a faster rate. Through glycolysis, you're producing NADH that wants to go to complex 1. The pyruvate that's being converted into acetyl-CoA is also, you're producing NADH from that, which wants to go to complex 1. The acetyl-CoA is running around the Krebs cycle, which produces more NADH that wants to go to complex 1. Right? By increasing the intensity of exercise and thus the ATP demand, the muscle fiber runs glycolysis at a faster rate to do what? The same thing as last time. Produce more NADH, and by that I mean more fuel for the electron transport chain. Because if you can provide the electron transport chain more fuel, then the electron transport chain can run faster, and more ATP via oxidative phosphorylation can be made from the electron transport chain, and ATP demand can be met. But in this circumstance, there perhaps is a bit of a problem with this. And it all is going to come back to oxygen. So as you increase the intensity of exercise, what also increases? Your heart rate, your respiratory rate. What are you trying to do? You're trying to get more blood and thus oxygen around your body to be delivered to your muscle fibers. And you think, well, what's the purpose of that? Well, think about it, right? If the intensity increases inside of the muscle fiber, meaning the ATP demand rises, and glycolysis is running at faster rates now, producing more NADH through glycolysis, through the conversion of pyruvate to acetyl-CoA, and through acetyl-CoA going around the Krebs cycle. Now you've got even more NADH during this higher intensity exercise going to the electron transport chain than you did during the more moderate intensity exercise, right? Because the ATP demand has risen, and now through increasing the rate of glycolysis, you're producing even more fuel for the electron transport chain. So what does the cell need more of? What does the cell need more of? It needs more oxygen, right? The cell needs more oxygen to extract more electrons from the fourth complex to allow all of this NADH and FADH that's being created to keep going through the chain at a faster rate. If you're producing more fuel over time for the chain, then you need to be able to run the chain faster to actually allow for that fuel to go through the chain. But here's what we think happens. In particular, there are certain muscle fiber types. We'll talk about this later on in the semester, but there are what are called fast twitch fibers and slow twitch fibers and fibers that exist in between, and especially the fast twitch fibers, which are heavily involved in high intensity exercise. The fast twitch fibers, we think there certainly comes a point, quite quickly actually, when they're activated, where they don't actually receive enough oxygen. And I'm not saying that they're receiving less oxygen than they were during the jog, because that's not the case. They're going to be actually receiving more. What I mean by they're not receiving enough oxygen is the fiber actually isn't receiving enough oxygen to remove enough electrons so that all of this extra NADH and FADH that's being created can keep moving through the chain. Because if you want this chain to run faster, to consume all of this extra NADH and FADH that's being created, then you need more and much more oxygen to be coming to the electron transport chain to be extracting more electrons. And that's what's trying to be accomplished during exercise when your heart rate continuously increases, so you pump more blood and thus oxygen around your body so that it goes into your muscle fibers. But in particular, with these faster twitch fibers, what we think happens is they don't actually receive enough oxygen to extract the number of electrons that they need to in order to keep all this fuel running through the electron transport chain. So what do you think happens? I mean, first of all, if more electrons are moving through the chain than can be extracted from the fourth complex, then they're all going to start to build up. Right? The electrons are going to build up throughout the chain because there's not enough oxygen extracting electrons from the fourth complex. And then are you going to be able to feed more of this NADH and FADH into the chain? Of course not. So now you've got all of this NADH and FADH that's being created that can't actually be fed into the chain because the whole chain is backed up due to a lack of oxygen taking away these electrons from the fourth complex. So what will begin to accumulate is a whole bunch of NADH and FADH within the matrix of the mitochondria. And this is going to have an influence, ultimately, over the amount of pyruvate and NADH that can actually enter into the mitochondria. So let's talk about why. All right, if a whole bunch of NADH is waiting to get into the electron transport chain, but can't, then what's going to start accumulating inside of the matrix of the mitochondria? NADH will. And what will you have less of in the matrix of the mitochondria? You'll have less NAD, because all of the NAD will be NADH, right? This NADH is waiting to get into the electron transport chain that's all backed up, like trying to pack more vehicles onto a jam-packed highway, right? It's very difficult to do that, impossible in some circumstances to do that. The vehicles just have to wait forever to actually get into or get onto the highway, which then causes a further backup of vehicles, right? It's perpetual. It's at least perpetual until something frees up the traffic, and that's not going to happen yet with the electron transport chain. So you have this NAD that's accumulating inside of the matrix waiting to get into the electron transport chain. And in the meantime, you don't have any NAD. We have a lot less of it. So what about that pyruvate that's coming in from the cytosol, the intracellular fluid? Can the pyruvate be converted into acetyl-CoA anymore? Not without NAD. If all of the NAD inside of the matrix is becoming NADH and it's stuck as NADH waiting to get into the electron transport chain, then you don't have the necessary coenzyme to convert pyruvate into acetyl-CoA. So what's going to happen to pyruvate in the matrix of the mitochondria? It's going to accumulate. The pyruvate will accumulate because it can't become acetyl-CoA due to the fact that NAD is lacking. At the same time, what's going to happen to the NADH that's coming in from glycolysis trying to get into the electron transport chain? It's also not going to be able to enter because we've already established this. The electron transport chain is backed up, so the NADH that's coming from glycolysis can't possibly enter. So the products of glycolysis, pyruvate and NADH, they can come in to the matrix of the mitochondria, but nothing can happen to them because the NADH can't actually enter in to the electron transport chain because, again, the electron transport chain is all backed up due to insufficient oxygen removing electrons from the fourth complex. And the pyruvate can't be turned into acetyl-CoA because a lot of the NAD that was in the matrix of the mitochondria is now NADH, right, waiting to get into the electron transport chain. So what's going to happen? You need a gradient in order for pyruvate and NADH to move from the cytosol, intracellular fluid, into the mitochondria. Right? There needs to be a higher concentration of NADH and pyruvate in the cytosol than there is in the mitochondria in order for them to be able to enter through these transport proteins. And as pyruvate and NADH accumulate inside of the mitochondria, there's not actually going to be a gradient for pyruvate and NADH to enter in anymore. So what's going to happen to pyruvate and NADH is they're going to begin to accumulate in the cytosol or intracellular fluid of the cell. Usually they would enter into the mitochondria. That's the natural place that they'd like to go. But because of all the reasons that we just discussed, because of NADH accumulating in the mitochondria waiting to get into the electron transport chain, that diminishes the gradient by which NADH and pyruvate can usually move into the mitochondria. So now they begin to accumulate outside of the mitochondria. And here's the next thing that they do. We think the accumulation of pyruvate and NADH allosterically activates the enzyme lactate dehydrogenase. When pyruvate and NADH accumulate outside of the mitochondria in the cytosol, we think that they bind to and allosterically activate the enzyme lactate dehydrogenase, which does what? Starts converting or reducing pyruvate to lactate and oxidizing NADH back to NAD. You have now begun what is called fast or anaerobic glycolysis. And it's because of the fact that these pyruvate and NADH molecules are accumulating outside of the mitochondria. And they're allosterically activating the enzyme that is going to begin the process of turning pyruvate into lactate and NADH back to NAD. And now the question becomes, why? To understand that, you first of all have to understand that the mitochondria was not, in this circumstance, meeting the ATP demand of the muscle fiber. Remember, this is like during a sprint, not a full-on sprint, but pretty high-intensity exercise. The ATP demand is very high. And due to insufficient oxygen coming to the fourth complex, you can't actually move enough of the NADH and the FADH through the electron transport chain for it to produce enough ATP through oxidative phosphorylation over time to meet the ATP demand. Okay? The point is basically that the cell is producing enough NADH and FADH to run it through the chain so that the chain, in theory, could produce enough ATP to meet the ATP demand. Right? Let's pretend that the ATP demand is 1,000 ATP per second. You're actually providing the chain enough fuel to make 1,000 ATP per second. But the problem is, of course, there's not enough oxygen coming to the muscle fiber to actually extract enough electrons from the fourth complex so that NADH and FADH can run through the chain at a fast enough rate to actually make this 1,000 ATP per second. Let's say maximally it can produce 500. Okay? That's just the fastest rate that the electron transport chain can go, and that's part of the reason that all of this NADH and FADH is accumulating, because there's enough coming to the chain for it to make 1,000 ATP per second, but there's only enough oxygen that can extract enough electrons from the fourth complex to allow it to run fast enough to make 500. So there's a lot more NADH and FADH coming to the chain than can actually be processed by the chain. The point is, through oxidative phosphorylation, you can make 500 ATP per second, but the demand is 1,000. All right, well, if we don't make up that other 500, what's going to happen to the muscle fiber? We've already discussed this. It's going to fatigue. The demand of ATP will be continuously higher than the supply of ATP, and the muscle fiber will fatigue. But what's happening within the cytosol with glycolysis? That might resolve this problem for us. By taking this pyruvate that's being created and reducing it to lactate, and by taking this NADH that's being created and oxidizing it back to NAD to feed back into glycolysis, you can keep glycolysis running independent of the mitochondria and the electron transport chain, right? That's why this is ultimately referred to as anaerobic or fast glycolysis. This system can produce 2 ATP, right, completely independent of oxygen. And by turning the pyruvate into lactate and the NADH back into NAD, you can keep this system operating endlessly independent of oxygen, and it can operate at a really rapid rate, and it can actually make up that other 500 ATP per second that's needed, perhaps, depends upon the intensity, to meet this ATP demand. So it's not that aerobic or slow glycolysis ever stops operating. It's that cells reach a point where the demand of ATP within the cell is higher than what that cell can produce within its mitochondria, through oxidative phosphorylation. And then what happens is the cell can transition to relying partly on anaerobic or fast glycolysis. And do you see what's happening here? Between the amount of ATP that we're making through oxidative phosphorylation, which is 500, and the amount of ATP that we're making through anaerobic or fast glycolysis, which is 500, perhaps we can make enough ATP to meet the ATP demand. Depends upon what the actual ATP demand is within the muscle fiber, and the type of muscle fiber that you're talking about, and all kinds of other things that we can't get into in this course. But these two systems are going to function together. And let me also explain why we need to turn pyruvate into lactate and NADH back to NAD, and not just allow glycolysis to keep happening and then endlessly allow pyruvate and NADH to accumulate. Because logically, you could think that that would be true, right? You could just think, well, who cares that pyruvate and NADH are accumulating? Why do you actually need to turn pyruvate into lactate and NADH back to NAD to keep this system going? Couldn't it just keep going anyways? And the answer to that is no, because if you were to allow just pyruvate and NADH to accumulate endlessly within the cytosol, right? We know that it can't enter in any meaningful way into the mitochondria because the mitochondria, the electron transport chains, are all backed up. So the NADH and the pyruvate can't really enter into the mitochondria. So if we just were to allow pyruvate and NADH to accumulate endlessly in the cytosol, this is the problem. All of the NAD in the cytosol would eventually become NADH. It's a coenzyme that's necessary to turn glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. You can't have that reaction of glycolysis without NAD. So eventually, all the NAD within the cytosol would become NADH, and you wouldn't be able to operate glycolysis anymore. The point is, you need to continuously regenerate NAD to actually keep glycolysis going. And that's the point of converting pyruvate to lactate. Reducing pyruvate to lactate regenerates NAD so that it doesn't fall within the cell, within the cytosol, and that keeps glycolysis actually running, right? Completely independent of the mitochondria and completely independent of oxygen. And that allows for this process to run at a really rapid rate and produce lots of ATP over a very short period of time. Hopefully now, when you look at these two things, you can see why anaerobic or fast glycolysis, in theory, should be able to produce so much more ATP over time compared to aerobic or slow glycolysis, right? First of all, you can make 2 ATP in just 10 steps. And second of all, the process isn't dependent on the electron transport chain and thus oxygen. In theory, it's completely independent of the mitochondria. So the rate at which it can run, since it has nothing really that bogs it down, like the amount of oxygen inside of the cell, since it has nothing that bogs it down, the rate at which it can operate is, in theory, phenomenally fast. So when ATP demands get really high inside of a cell, this becomes an ideal system. I know my numbers of 1,000 ATP per second required versus 1,000 being made in this circumstance isn't perfect. You really need a separate course to go through a multi-step process to make complete sense of how all of this works. And you also have to compare different muscle fiber types to each other, which we'll do a little bit of in this course, but there's just it's a separate class to really fully understand this in its entirety. If you can get an idea here of what causes the transition from solely aerobic or slow glycolysis to a combination of aerobic and anaerobic glycolysis, then I think it's mission accomplished. And even better yet, why? Right? Because the ATP demand is very, very high inside of the fiber, and that ATP demand can't be met through oxidative phosphorylation within the mitochondria. So you're going to need another system that can produce ATP very fast, independent of oxygen and the mitochondria, and that is what anaerobic or fast glycolysis can do for you. And then you might finally ask, what would cause the muscle fiber to finally fatigue? In my example, I'm telling you that oxidative phosphorylation within the mitochondria is making 500 ATP per second, and anaerobic glycolysis, which is happening in the cytosol, is making 500 ATP per second. And between the two of them, they're actually meeting the ATP demand. Okay, this could happen in somebody, again, who's a very, if this is a very fast run on a treadmill, this could happen in somebody that's like an elite runner for sure. The amount of ATP that's probably being made from anaerobic or fast glycolysis would probably be a lot higher than 500. Maybe the ATP demand is actually 1,500, and anaerobic or fast glycolysis would be making 1,000 of the 1,500 ATP. That would be a more realistic, number numerically. So oxidative phosphorylation, 500 ATP per second. Anaerobic fast glycolysis, double that, 1,000 ATP per second. All right, what you would have to do to get fatigue to set in is you'd have to increase the intensity or the ATP demand to an even greater degree. Imagine beginning to sprint. As you're contracting those muscle fibers as forcefully and as frequently as you possibly can. Right? What's going to happen to the ATP demand? It's going to rise to 2,500 or something. Right? It's going to go through the roof. And anaerobic or fast glycolysis plus the phosphagen system can probably meet this ATP demand for a short period of time. The phosphagen system can make ATP phenomenally fast because it's a one-step system, but it runs out very, very quickly. So eventually what's going to happen is, especially once the phosphagen system is depleted during this sprint, the ATP demand is going to be substantially higher than what anaerobic or fast glycolysis can produce on its own, plus aerobic or slow glycolysis, which isn't very much compared to what the total ATP demand is during this sprint. So you've got to get to a point where the ATP demand is higher than what the muscle fiber can actually produce. And that certainly happens, especially in our fastest twitch fibers. We reach a point where the ATP demand is even higher than what anaerobic or fast glycolysis can produce. And that's when we think really fatigue sets in. Okay? It's when the total demand of ATP within the muscle fiber is higher than what it's actually able to supply or accomplish. And at that point, let's say total anaerobic or fast glycolysis can produce 1,500 ATP per second. That's its maximum in this example. And aerobic or slow glycolysis isn't going to change. It can produce about 500. Between the two of them, you're producing 2,000 ATP per second, which is not 2,500. So the demand of ATP is endlessly higher than the supply. And then what's going to happen? The molecules that cause fatigue are going to accumulate in the muscle fiber, and the muscle fiber will fatigue. And when it fatigues, the ATP demand will fall, because if the muscle fiber isn't contracting as forcefully and frequently, which is what happens during fatigue, then the ATP demand will fall and it'll get closer to supply, and you'll be back to a state of, tough to call it equilibrium, but you're certainly back to a state of where the demand of ATP meets the supply. And there you have it. You've seen a variety of different systems that most of the cells in your body use to make ATP. Hopefully you have an idea of how and why a cell transitions between these systems and why one system would dominate over the other. One thing, of course, the big thing to take away from this is the objective of a cell is always going to be to meet its ATP demand. Whatever the ATP demand of a cell is, it has to meet that demand. And it has many different systems for doing that. And we didn't even talk about all the systems. One of them is called beta oxidation, which is the breakdown of fatty acids actually to make ATP, and that's involved here too. But it's one of the things that we didn't have time for. And at the end of the day, all these systems work together. It's not that one works by itself. Don't ever believe that, because it couldn't be any further from the truth. These systems work together to meet ATP demands. Different systems will dominate over other systems depending upon what that ATP demand is, and of course the circumstance, but all of them work together. There's so much more to say about metabolism that we didn't get to, and I hope if this kind of stuff sparks your interest, I hope you take more advanced physiology courses if you get a chance, or biochemistry. Advanced biochem goes into some of this as well.